sklearnbaseEstimator. Description: the base estimator class in scikit-learn sklearn is the fundamental building block for creating custom machine learning estimators. It defines the basic structure and methods that all estimators in scikit-learn should adhere to. Inputs: data. The input data for training or predicting, typically represented as a NumPy array or a pandas data frame. Target: for supervised learning, the corresponding labels or target values associated with the data. For supervised learning tasks. Outputs: trained model. After training, the estimator learns a model based on the input data and target values, which can then be used for predictions. Predictions when applied to new data. The trained model generates predictions. Steps: initialization. The init method is called to initialize the estimator with any required parameters. Fit. The fit method is used to train the estimator on the input data and target values. Predict. The predict method is used to generate predictions for new data. Metrics: accuracy, a measure of the proportion of correctly classified instances in a classification task. Precision, the ability of the model to correctly identify positive instances. Recall, the ability of the model to correctly identify all positive instances. F1 score, a harmonic mean of precision and recall. Mean squared error, MSE, a measure of the average squared difference between the predicted and actual values in regression tasks. R squared, a statistical measure that indicates the proportion of the variance in the dependent variable that is explained by the independent variables. Visualization plots. Confusion matrix, a visual representation of the performance of a classification model, showing the number of correctly and incorrectly classified instances. ROC curve, a plot of the true positive rate against the false positive rate for different threshold values. Precision recall curve, a plot showing the relationship between precision and recall for different threshold values. Learning curve, a plot that shows the performance of the model as a function of the size of pay. Training data. Fine-tune parameters. Regularization parameters, e.g., L1, L2, used to prevent overfitting by penalizing complex models. Learning rate, a parameter in gradient-based optimization methods that controls the step size for each update. Number of trees for ensemble methods, the number of decision trees used in an ensemble method like random forest. Maximum depth of trees, the maximum depth of individual trees in ensemble methods. Uncertainty methods. Confidence intervals provide a range of values within which the true value is likely to lie. Bayesian inference incorporates prior knowledge and uses probability distributions to estimate the uncertainty in model parameters. Bootstrapping, resampling with replacement to estimate the uncertainty in predictions. Challenges and fixes. Challenge 1: overfitting. The model learns the training data too well and fails to generalize to new data. Sample use case that resulted in challenge 1: using a complex model with too many parameters on a small dataset. Fixes to challenge 1: use regularization techniques, e.g., L1, L2, to penalize complex models. Use cross-validation to evaluate the model's performance on unseen data. Simplify the model or use a smaller dataset. Challenge 2: underfitting. The model is too simple and fails to capture the underlying patterns in the data. Sample use case that resulted in challenge 2: using a linear model on a nonlinear dataset. Fixes to challenge 2: use a more complex model that can capture nonlinear relationships. Add more features to the dataset. Increase the complexity of the model by adding more layers or neurons. Challenge 3: data leakage. Information from the target variable is unintentionally included in training data, leading to artificially high performance. Sample use case that resulted in challenge 3 using a feature that is derived from the target variable during training. Fixes to challenge 3. Carefully select features that are not correlated with the target variable. Use techniques like train test splitting or cross-validation to ensure that the training and testing data are independent. Use domain knowledge to identify and remove features that are likely to leak information. Challenge 4. Imbalanced data. The target variable is not evenly distributed across the classes, leading to biased models. Sample use case that resulted in challenge 4. A dataset where one class is significantly more frequent than the others. Fixes to challenge 4. Use techniques like oversampling, undersampling, or synthetic data generation to balance the dataset. Use class weights to penalize misclassifications of minority classes. Use appropriate metrics that are robust to imbalanced datasets, such as F1 score or AUC.